this in Physics 1, but you've certainly experienced it if you've driven anywhere when you hear a fire engine or ambulance or a police car moving towards you and then away from you. You hear the pitch of the siren change, and the reason is that car is moving at a reasonable fraction of the speed of sound. Interstate speed is about 10% of the speed of sound, for example. The Doppler effect for light works the same way, only simpler. For light, all we care about is the relative motion between the source and the observer. For sound, what matters is not only that relative motion, but also who's doing the moving. The reason there's a difference, and the reason we can tell, is there is an absolute standard of rest for sound. You have to have air if you have sound, and whoever's moving can tell because there'll be wind in their face. So you can't both say, oh, I'm sitting still and the other guy's moving. One of you is actually going to be feeling a breeze. So for light, the situation is much more symmetric. In this picture here, you can see, imagine we have a green face that's emitting flashes of light periodically while it moves from left to right. What we notice are these flashes are expanding outward at the speed of light. You notice they're clustered over here. That's because the older ones were emitted when the green face was further over here to the left. The largest ones are the oldest ones. The face on the far right, the blue face, is going to see a lot of these waves all at once. It'll measure a higher frequency for the light than the green guy who emitted the light. The red face over here on the left will see these waves much more spread out, so it's fewer of them per second hitting the red guy. He'll say the frequency is lower. So this is what we would call the regular Doppler effect. This is called blue shift when you receive a higher frequency than was sent, and it's called red shift when you receive a lower frequency than was sent. The yellow observer, it may look like they shouldn't see any change at all because if we were moving in a circle, it would be more obvious. With the regular Doppler effect, if they're at the center of a circular racetrack, we don't expect them to hear any change because you're not getting any closer to or further away from the ambulance. However, there's still the relativistic red shift because you would see the clock and everything associated with it carried by the green person to be slow. So there's what's called a transverse redshift in relativity. The regular redshift would look like this. We would say motion away from the observer is positive v and motion towards the observer is negative v. We can put in our numbers, put in the wavelength at the source, and we can find the wavelength at the observer. For the transverse shift, if we wanted to find the frequency, for example, which is related to the wavelength as it always has been, lambda times frequency is speed of light. For the transverse Doppler shift, we just take our frequency and divide by gamma.